Okay, I've reproduced the graph. Again, we're graphing f of x is x cubed minus 3x squared minus 9x plus 4. Just using information about the first and second derivative, not using our graphing calculator at all. Previously, we took the first derivative. We found critical numbers. Those are places where the derivative is 0 or undefined. We found that the critical numbers were -1 and were 3. And these points are the points with the x-coordinates of those critical numbers. We found the critical numbers by setting the derivative equal to 0, so we know they're horizontal tangents here and here. There were no places where the derivative was undefined, so there are no sharp corners. Okay, and I formed a table. I put my critical numbers, remember, -1 and 3, into on the number line, and those formed 3 intervals, and I picked a test number in each interval, and I looked to see if the derivative was positive or negative, and that told me if the function was increasing or decreasing. Let me see now if I've got the shape of the graph right. Let me take the second derivative and let me check the concavity. So I'll take the second derivative, and I get 6x minus 6. Now, repeat exactly the same process that I did previously for the first derivative. You want to see where is the second derivative equal to 0, and you want to see where is the second derivative undefined. Now, we will not call the numbers that result from this analysis critical numbers, because critical numbers are just numbers where the first derivative is 0 or the first derivative is undefined. The first derivative. Critical numbers come from the first derivative. Okay? So what we get down here will be candidates for our points of inflection. Okay, set this second derivative equal to 0. Solve for x. I get x equal 1. Where's the second derivative undefined? Nowhere. 6x minus 6, you can put in any real number for x and get a real number. So put this number that resulted on a number line. I've got 2 intervals. The intervals are minus infinity to 1, that's this first interval, and 1 to infinity. I pick a test value k in the interval. I look for the sign of the derivative evaluated at k, and I use that to determine the behavior of my function on the interval. So pick a number less than 1. How about 0? When I plug 0 into the second derivative, 6 times 0 minus 6, that's negative. All I care is the sign. Is it positive or negative? So this tells me the second derivative is negative on this interval, negative infinity to 1. So that tells me f is concave down. Pick a number bigger than 1. How about 2? Plug 2 into the second derivative. I get 6 times 2 minus 6. That's positive. So this tells me f is concave up. The second derivative being positive means the graph is concave up. So notice a point of inflection is where concavity changes, and concavity is changing here where these 2 intervals coincide. So concavity is changing changes from what? From concave down to concave up at x equal 1. So 1 f of 1 is a point of inflection. Okay, now let's see if my graph has the right concavity. If it doesn't, I'll fix it. So it's important to plug the point 1 in, since that's going to be a point of inflection, into my function to see how high to plot that point. The only numbers I'll ever plug into the function are x-coordinates of points of inflection and critical numbers. So f of 1 is 1 cubed minus 3 times 1 squared minus 9 times 1 plus 4. So that's negative 2 minus 9 is negative 11 plus 4 is negative 7. So 1, negative 7. Okay, that point should be on the graph. Okay. You know, a real easy point to get would be a y-intercept. If x is 0, put 0 into f of x, you get 0 minus 0 minus 0 plus 4. So a y-intercept's a good point to get. I know I said we're only going to plot critical numbers and points of inflection, but that was just low-hanging fruit, so I'm going to grab it. Okay? Now, my graph is supposed to be concave down from negative infinity to 1. From negative infinity to 1 is supposed to be concave down. Alright, this is concave down. But it's supposed to continue being concave down until here. Remember, concave down means the tangent lines are on top. And this point is where it starts being concave up. And it's concave up from 1 to infinity. You know, just with the first derivative information, we did a pretty good job of getting the graph. That's often true. It's not a perfect graph, but it sure does beat plotting tons of points.